Yeah, thank you. Okay, so good afternoon, everyone. So yeah, we are done with all the results in chapter 8, all the major results. I skipped a couple of very easy propositions. You can take a look at them on your own. They are really not difficult at all. In fact, I think the content of all of them, we have essentially covered it. So the next thing in line is dependence classes in bricks. That's what the chapter is called. But yeah, that's not necessarily my viewpoint of the contents. So what I will do today is I will try to summarize some of the main results that are proved in this chapter, and we may even see proofs of some of them modulo some technical lemmas and propositions, right? But let's already discuss what we know, right? So in chapter 8 we already covered a few things from chapter 9 because I got too excited. So one such thing is the structure of structure of mutual dependence in bricks. So if I have a brick G and I have distinct mutually dependent edges, then we discussed why the graph actually looks like this. After deleting E and F, what you have is a bipartite matchable graph, and E's ends are in one color class and F's ends are in the other color class, right? So in fact it's if and only if, right? The other direction is clear. If my graph has this structure, then clearly the two edges are mutually dependent. So is bipartite, matchable, and of course connected, because I deleted two edges from a three connected graph, right? So this is what we have for mutual dependence in bricks, right? So that's the way I would like to remember this. This is basically a complete characterization of and hopefully everybody remembers the proof of this. What we first did is we went to mutual dependence in matching covered graphs, right? And we observed that for all the odd components after deleting the barrier, what you have is tight cuts. Each odd component is a shore of a tight cut. But because this is a brick, each of them has to be trivial. Therefore, it is just a bipartite graph, and we are done. That's how we proved it. Okay, so that's 9.1 is already QAD. A consequence of this that we discussed is that in a brick, you simply cannot have a dependence class or an equivalence class that is larger than 2. Because the moment you have 3 edges, you will get a 2-edge cut by considering the symmetric difference of 2 cuts, right? So therefore, in a brick, every equivalence class, it doesn't have to be minimal. In general, this is a true statement for minimal classes. Not minimal, removable classes. Right, we proved in chapter 8 that a removable class in any matching covered graph is either a singleton or a doubleton, right? But here this is true for every equivalence class. Every equivalence class is singleton or doubleton. This also we proved. Right? Yeah. Recording is going on, right? Yeah, thanks. Okay, good. So in a brick, every equivalence class is singleton or doubleton. Right? In general, an equivalence class could be arbitrarily large. In fact, you may say bricks are 3 connected bicritical. What about just 3 connected graphs? Can we do something? Well, no. For any arbitrary integer k, any positive integer k, and another positive integer L, you can construct a matching code graph that is k connected and has an equivalence class of cardinality L. Right? So in general, you cannot control the cardinality of equivalence classes. Right? So bricks are not just 3 connected, they are also bicritical. All these things are important. Right? Okay.
Just bicritical.
Just in a bicritical graph. Not sure. Think about it. Yeah. Just in a bicritical graph, I don't think I have an immediate answer to that. Yeah, but probably the same paper where we prove this for any two integers k and L, maybe some of the same techniques can be used. So in fact, the main contribution of that paper, I am forgetting the abbreviation. I think it's Foulian Blue, myself, I don't remember, 2020 I think. I think there's 4 authors. The main contribution in my opinion of that paper was to basically show that, basically understand when you splice two matching code graphs G1 and G2 to obtain another matching code graph G, how do the equivalence classes of G look given the equivalence classes of G1 and G2, and vice versa. Given the equivalence classes of G, can you sort of compute the equivalence classes of G1 and G2, where the splicing may or may not be tight. So for both tight cuts and separating cuts, what can you say? And if you understand that well enough, then you can actually construct, for any k and L, you can construct these graphs that are k connected and equivalence class of cardinality L is there, right? So maybe if you look at the same paper, you might be able to also construct bicritical graphs with large equivalence classes, but I'm not sure. Maybe that is worth thinking about. Yeah, okay. And the other contribution of this paper was an incorrect proposition that became a chapter in Narayana's thesis, or the correct answer to that question. So, anyways, good. Let me show you an example of a graph that has a large equivalence class. So, in fact, yeah, this is a nice example. Here's a matching code graph with a sort of big equivalence class, where big is just 3 in this case. Okay. So far so good. We'll add a few edges now. We'll label the vertices 0, 1, 2. I'll draw the remaining edges in another color. They are somehow the more interesting edges. Oh, actually, I wanted to color this as well. Here's the graph. See if you can find an equivalence class that has more than 2 edges. And another question I have is, construct an example where this is not matching covered for this proposition. So here the example should be a brick with 2 mutually dependent edges. When you delete the 2 edges, you will get a bipartite matchable connected graph. What I want is, it should not be matching covered. So, some of you have figured out that there is an equivalence class of cardinality exactly 3. Right? There is an equivalence class of cardinality 3 in this example. But if it were a minimal class, then it would contain an even 2 cut, and its deletion would disconnect the graph. Right? If it were a minimal class, it would contain an even 2 cut, and the deletion of the class would have to disconnect the graph. Right? Observe that when you delete the 3 edges that you have identified, that you have found, you actually don't disconnect the graph. Is that correct? The graph is still connected. Yeah? That's one way to see that this must not be a minimal class. Of course, there are easier ways to see that it is not a minimal class by just observing that there are specific edges that depend on this class. Right, so you have found an equivalence class Q of cardinality 3, and there are specific edges that depend on Q. Right? Those are 3, 5 and 3, 6. Observe that 3, 5 depends on Q and 3, 6 depends on Q. I haven't yet told you what Q is, but well, most of you know what Q is, right? So, right, okay. And one way to sort of understand how this graph is constructed is to consider specific tight cut contractions. Let's see. Is this a tight cut? This has to be a tight cut, is it? No, wait, let's see.
3, 7 is a barrier.
What is a barrier?
3, 7.
3, 7 is a barrier. If I delete 3 and 7, I have one odd component here and I have another odd component here. Cool, good, exactly, thanks. So, here is a tight cut. Draw the 2C contractions for this cut C. And try to see what happens to, so let's say the 2C contractions, let's say we call them G1 and G2 after shrinking the corresponding shore. Try to see what the restriction Q1 and Q2 look like. Q1 in G1 and Q2 in G2. In some sense, what has happened is Q1, which is the restriction of Q to G1, is an equivalence class in G1, and Q2 is an equivalence class in G2. But somehow the two equivalence classes have merged into a single equivalence class in the resulting graph G. That is basically what has happened due to the splicing. And this is one of the questions that is answered in that paper I mentioned. So we can draw the graphs. Was that one contraction? The number of edges incident at the shrunken vertex should be 1, 2, 3, 4, 5. Yeah, that's one contraction. That is one C contraction. This is G1. And the other C contraction is Three has two parallel edges, and from 7 I have 3 edges going here. Wait a second. What am I doing? 3 also has edges going to the contraction vertex, yeah. 7 has how many edges going? 7 has 1 going to 2. And this, yeah, okay, this is fine. And yeah, this should be degree 5 vertex, those are these 2 edges. Is that right? What did I do? 3 to 7. Ah, that is not parallel. There are no edges actually. From 7 there is an edge to 4. There is no these. Yeah, these are not right. Yeah, sorry about that. Yeah. Yeah, sorry about that. Now is it okay? Good. Yeah. Those are G1 and G2. Yeah. And right, can I write down now Q? Right, Q is the remaining 3 yellow edges that are not here. That's our Q. Q is 0, 1, 8, 9 and 4, 7. Observe that that's Q. If you look at the restriction in this graph, Q1 is just this edge. And in this graph, the restriction is 4, 7 and 8, 9. That's Q2. Yeah? Observe that Q1 is an equivalence class here actually. This is not mutually dependent with any other edge. There may be dependence, but not mutual dependence. This is an equivalence class. Here, this is an equivalence class. Observe that 4, 7 depends on 8, 9 and 8, 9 depends on 4, 7. Yeah? Okay? And Q1 depends on, if you take Q1 in a perfect matching, this edge in a perfect matching, then you must take one of these 2 edges. And likewise, if you take Q2 in a perfect matching, you must take one of these 2 edges. These 2 are exactly these 2. In the original graph, they are exactly the same edge. That's basically what's going on. You have, when you are doing the splicing, it's a tight splicing first of all, right? You get a tight cut. And the class Q1 depends on, or doesn't really depend on, the depends is not the right word. Every perfect matching containing this fellow contains one of these 2. And in fact, precisely one of these 2. And likewise, every perfect matching containing this fellow contains precisely one of these 2. And that's basically why the 2 equivalence classes are merging into a single equivalence class in the resulting graph. Anyway, this is sort of the content of one of the propositions in that paper. I sort of just remember because I wrote that proposition many years ago. Yeah. So using this idea, you can actually now construct matching covered graphs with large equivalence classes, and you can also find a way to bump up the connectivity. You can do all these things simultaneously, and that's how these constructions are done, right? So that was actually an open problem in one of the papers. Are there matching code graphs that are arbitrarily large, that have arbitrarily high connectivity and arbitrarily large equivalence classes? And the answer is yes, there are such graphs, right? So this is just one example. In the notes in Lucchesi-Murthy, they have written that they had actually found this graph once upon a time and they had forgotten about it. So yeah, it seems that they already knew that you could construct large equivalence classes. I'm not too sure how much they thought about bumping up the connectivity. That was a specific question asked by Hay et al. I forget who Hay et al. Are, but anyways. So this is one example. The point is, in a brick, this is not possible. Every equivalence class is singleton or double. And the other question I have here is, can you construct a graph, a brick, where this fellow is not matching covered? Well, the idea is to reverse engineer it. That was a question that was asked by these authors. Hay et al. Had asked a question, I think in 2018 or something. Can you construct matching code graphs with arbitrarily large connectivity and large equivalence classes? And the answer is yes. Using this approach, basically you just have to understand how splicing will create large equivalence classes. And if you understand that well enough, then you can also bump up the connectivity. Yeah. Right? Okay. But now let's go to the other point. Can we construct a brick with a pair of mutually dependent edges, so that when you delete the two edges, you will get a bipartite connected matchable graph, but it shouldn't be matching covered. So one way to go about such a question is to just create your favorite bipartite matchable graph that is not matching covered. So do you have a favorite bipartite matchable connected graph that is not matching covered? And you know that when you add the two edges, E comma F, the graph should become bicritical, but also three connected. So what you can do is you can already try to make the H graph sort of well connected. So can you make a three connected bipartite matchable graph that is not matching covered? And it's also simple. Three connected bipartite matchable graph that is not matching covered. See if you can make one. I have a favorite. Almost like a favorite. So if you have constructed such a graph, if you have constructed a graph like this, now see if you can add two edges, one in one color class and one in the other color class, to make a brick. Right? And if your graph is symmetric enough, then checking bicriticality should be not too difficult. So one way to go about this is to take two copies of K33. I wish I could just clone this, but I can't. So, can you add some edges to two copies of K33 to get a three connected bipartite graph that is not matching covered? Right. Yeah, exactly. All going from white to black. Yeah, right. So, if you have two copies of K33, you can simply add these edges. Now you have a three connected bipartite matchable graph that is not matching covered. Now can you add two edges to make it a brick? Well, first of all, the two edges have to be matchable, and in fact all these edges have to become matchable once you add those two edges, right? Because a brick is matching covered in particular. So if you think about it that way, then there are not too many ways to actually try. Right? If you want all these edges to be matchable, then, and you are only allowed to add two more edges, one joining this color class, one joining this color class, then it's clear that to make this edge matchable, you must add an edge like this. There's no choice really, right? You must add an edge here, and by symmetry you must add an edge here. This is your example. This is a brick. Now you can check bicriticality. It's not too difficult. Observe that you never have to check bicriticality for adjacent pairs of vertices. Once you know the graph is matching covered, you only have to check for non-adjacent pairs. Then it's quite straightforward.
How do we, I mean, all these edges will be in the matching.
So now let's see. Now you can find a perfect matching ending this edge. I can match this fellow here, and let's see. It actually follows by symmetry now that every edge is in a perfect matching. Right. So this turns out to be one example of a brick where you can see that two mutually dependent edges does not mean that after deleting the two edges you get a bipartite matching covered graph. But you get a bipartite graph that is matchable. Right? If you got matching covered, then it would actually be what we call a near bipartite graph. That's basically what I'm trying to demonstrate. That just because a brick has mutually dependent edges does not mean it is near bipartite. In fact, I think this graph probably has no so-called removable doubleton, if I'm not mistaken. This is actually a brick that is, I think, not near bipartite. For that, you will have to check that there is no pair of edges whose deletion gives you a bipartite matching code graph. DIY. Maybe false. I don't know. Is there any removable doubleton? pair of two edges whose deletion gives you a bipartite matching code graph. In fact, yeah, removable doubleton technical will give you matching code graph. The fact that it is bipartite will follow from here. Yeah. Okay, so those are a few things. Another quick consequence, basically everything is just proved at this point. In a brick, every minimal class is removable. Think about it. In a brick, every minimal class is removable. Because it's going to be cardinality 1 or 2. And then of course it is removable. You can't lose connectivity by deleting one or two edges. Yeah. Okay. One more cool fact. If I give you two distinct equivalence classes, each of cardinality 2, then what is the union? G is a brick. Supposing I tell you that Q1 and Q2 are distinct equivalence classes of cardinality 2. Then what can you say about this set? Each of them will give you a drawing like this. Each of them will give you a drawing like this, and this is a cut of the graph, right? Yeah. Okay. So what is the union of Q1 and Q2? It's a cut. Observe that for Q1 you will get this drawing. The edge set of the graph minus Q1 is a cut of the graph. The edge set of the graph minus Q2 is also a cut of the graph. Their symmetric difference is exactly Q1 union Q2. Do you all agree? Edge set of the graph minus Q1, symmetric difference edge set of the graph minus Q2 is exactly Q1 union Q2. So that's a forecut of the graph. This actually proves some nice things. This means that if I tell you I have a brick, for example, can we now use this to solve this case? If there was a removable doubleton in this graph, if there is a removable doubleton in this graph, yes, supposing there is a removable doubleton or any other doubleton, any other two mutually dependent edges. So this is one pair, E1 and E2. Let me call it E1 and F1. Q1, thank you. Alright, so coming back to this example, Q1, E1, F1. Do you all agree this is a pair of mutually dependent edges? In fact, I don't even need equivalence class. I can just use a pair of mutually dependent edges. It may not be a whole class, right? So E1 and F1 are mutually dependent. If I had another such pair, E2, F2, then E1, F1, E2, F2 would be a forecut of the graph. But remember, G minus E1 minus F1 is actually 3 connected. That is how we constructed this graph. You all agree that if I delete E1 and F1, I have a 3 connected graph. There is no 2 cut there. So therefore, what we have just proved is, using this, we have just proved that there is no other pair of mutually dependent edges in this graph. You have to check that this is a brick actually. Once it is a brick, you can simply apply this. So in fact, there is no other pair of mutually dependent edges. Therefore, there is no removable doubleton. Therefore, this brick is actually not near bipartite. So we just solve the DIY. Yeah. So no. Otherwise, you would have a forecut containing these two edges. We use a slightly more general statement than this one. This statement is also true for pairs of mutually dependent edges. Right. Okay, all of this is done. If I give you a removable doubleton, which just means a removable class of cardinality 2. We know that every removable class by chapter 8 is cardinality 1 or 2. If I give you a removable doubleton, I think I already mentioned this earlier. Supposing G is a brick that has a removable doubleton. R. Let's assume it has a removable doubleton R. Then what can we say about G minus R? All this is fine. It is a bipartite matchable connected graph. That much is clear. But this is not only this is not only a pair of mutually dependent edges. This is a removable doubleton, which means it is a whole class. There are no other edges in this equivalence class. That means G minus R is matching covered. Yeah. Yeah. This was actually proved by Lovász, but now there are more general statements which will be proving. So this is a special case of something that was proved by Lovász, or equivalent to something that was proved by Lovász. But we will see a more general statement than this. In particular, observe that the number of bricks from G to G minus R has gone down by 1. G is a brick, so B of G is equal to 1. This is bipartite and matching covered, so we can talk about B function. So B of G minus R is 0. This is not a coincidence. This is a manifestation of a more general statement. So observe that B of G minus R is actually equal to B of G minus 1 which is equal to 1 minus 1, which is equal to 0 in this case. Yeah, but we will see that this is more general than this. Okay, good. All right. Right, so we have proved a bunch of statements. Right, everybody is okay with all these? Okay, good. So in fact now I've gotten a bit ahead of myself, so let me just go there. Okay, any questions or concerns so far? All good? Yeah? Okay, let me make some space. I'll erase these examples. So let me just tell you the more general statement of 9.5. In general, what happens when you delete a removable doubleton, right? So there are only two types of removable classes in life, singletons and doubletons. 9.9 deals with doubletons. G is a matching covered graph that has some removable doubleton. It has a removable doubleton. Then the question is, how are these two quantities related? And it is exactly what we just saw. Turns out, what you see in the case of bricks happens in all matching covered graphs. It goes down by 1. So, we will prove in this chapter that this always goes down by 1 on deleting a removable doubleton. Okay. So B, the number of bricks of a matching covered graph, that is definitely an important parameter. I think I don't need to really justify that at this point. It comes up in a bunch of formulas, including perfect matching, polytope, etc., etc. However, there are cases where the Peterson graph plays a special role. So there are cases where you count all bricks once, but you count the Peterson brick twice. Okay? One such example is going to come up when we study ear decompositions in chapter 11. But already in an earlier lecture, we kind of discussed ear decompositions. We saw ear decompositions of the Peterson graph. And if you recall, ear decompositions of the Peterson graph, they require two double ear additions. What will happen is you start with an 8 cycle, because you have to start with a conformal cycle. The only conformal cycles in the Peterson graph are the 8 cycles. 6 cycles are not conformal. You start with an 8 cycle, then you have to add a double ear. That will give you a bi-subdivision of K4. And at this point, you are missing 3 edges. Let me just remind you of that drawing. This is a drawing we had a few lectures ago. This is the beautiful bi-subdivision of K4 you will get when you add the first double ear. You first start with an 8 cycles. You start with any of the 8 cycles here by deleting, for example, if you delete this, now you have all the 10 vertices. if you delete these two vertices and this edge, what you have is an 8 cycle. So you can start with that 8 cycle or any of the other 8 cycles you see here by symmetry, and then you add a double layer, this single edge and this path of length 3. That is your first double layer. You now have bisubdivision of K4, which is a matching covered graph and is a spanning subgraph of the Peterson graph. Yeah, you have all the vertices here. Now at this point you are missing exactly 3 edges in life. Those are symmetric actually. This fellow, and this fellow. Amongst these 3 edges, amongst these 3 pink colored edges, you cannot add any one of them. That will not give you matching covered graph. But you can add any 2 of them simultaneously. That will give you a matching covered graph. That is Peterson minus 1 edge. Then you add your last edge and you are done. So in any ER decomposition of Peterson graph, you can convince yourself later. And of course this is before discussing ER decompositions formally, which will happen in chapter 11. In any ER decomposition, you need exactly 2 double layer additions. The first one will give you bisubdivision of K4 and the second one will give you Peterson minus 1 edge. Turns out Peterson is the only brick with this property. Every other brick on Earth, well, I don't know, Earth, every other brick requires exactly 1 double layer addition. There is an ER decomposition for any brick that uses exactly 1 double layer addition, not the Peterson graph up to multiple edges, right? So therefore, this is one case. If you want the number of double layers, the minimum number of double layers, the answer is B plus P. In any matching covered graph, the minimum number of double layers required across all ER decompositions is B plus P. Number of bricks counting Peterson twice. That's the answer, right? And observe that B plus P is 0 if and only if the graph is bipartite. So for bipartite graphs, we don't need double layers. That is why we cover bipartite ER decomposition in SGT, not in this course. Prerequisite, right? So this is one example where you need the function B plus P, and therefore, while we are at it, let us also settle this. We will prove both of these. We will prove that the number of bricks goes down by exactly 1 when you delete a removable doubleton, and the number of bricks counting Peterson twice also goes down by exactly 1. Yeah? We haven't proved this yet. We will prove this later. Yeah? Yeah? But this is a generalization of what Lovász had already proved. For a brick, you get a bipartite matching covered graph. Okay? Yes.
Doesn't that mean like P of G minus R equal to P of G?
Yeah, can you repeat that?
Doesn't that mean P of G minus R
Yes.
is equal to P of G?
P of G minus R is equal to P of G.
P plus P of G minus R is B plus P, right?
P of G minus R is equal to P of G. Is this your claim?
Yep.
Let me think.
Like, isn't P plus P just P of G plus P of G?
Yes, it is. Yes.
So
Yeah, I did not define it. Sorry. Yes.
okay, so then you can just plug the P of G. The minus 1 will go away.
Okay, I see your point. So the number of Peterson bricks in G minus R is the same as the number of Peterson bricks in G. Yeah, looks like. Yeah. So by deleting a removable doubleton, you should not be able to change the number of Peterson bricks. Yes, and I think I find that believable. Yes. Yeah. Yeah. That seems believable to me. To change the number of Peterson bricks, I think you should delete a removable edge, not a removable doubleton. That is what happens in the Peterson graph. The Peterson graph, B is equal to 1 and P is equal to 1. But if you delete one edge, you will get two bricks, each isomorphic to K4 up to multiple edges, and no Peterson anymore. So B will increase by 1 and P will decrease by 1. B plus P will remain the same. Yeah, okay. Yeah, so I think this is fine. Now, honestly, I find this B plus P fellow very confusing. Okay, so anyway, let me just define it. B plus P of G is defined as B of G plus P of G, where P of G is number of Peterson bricks. And I say number of Peterson bricks because it is Peterson graph up to multiple edges. That's generally how we think of it, right? So when we do the tight cut decomposition, we don't throw away the multiple edges. So P of G doesn't mean number of bricks isomorphic to simple Peterson. It means number of bricks isomorphic to Peterson up to multiple edges. Right? So we'll be proving this soon in this chapter. Yeah. Okay. This is the so-called monotonicity of B with respect to deletion of removable doubleton. We'll just call it monotonicity of B, and we'll not talk about B plus B too much with respect to deletion of removable doubletons. But this of course raises the question, what about deletion of removable singletons, also known as removable edges? What happens to the B function and what happens to B plus B? Yeah? Let's think about a brick, because that is what we did here. Here we first thought about brick, we already proved this, and then we saw the more general statement. Yeah? So let's think about a brick. Supposing I give you a brick that has a removable edge. So G is my brick, E is a removable edge. What happens to G minus E? B of G is equal to 1 because G is a brick. I've deleted a removable edge, I have G minus E. How does the number of bricks, can it become 0? Can G minus E be bipartite? Well, if it is not bipartite, then you already have some information about B of G minus E. Right? So can it become bipartite on deleting one edge? Deleting one edge will not make it bipartite. In fact, deleting one vertex will also not make it bipartite. I believe this should follow from some of your assignment problems. If I delete one vertex and I get a bipartite graph, that seems strange. That shouldn't happen, right? Does it follow from some assignment problem?
That's the reason.
Yeah.
There's a theorem of proposition in the book.
It is a proposition in the book itself. I think we discussed it earlier.
G minus V is bipartite, then G itself is.
If G minus V is bipartite, then G itself is bipartite. That is something we discussed earlier. Exactly. Right?
You can find some edges that are not matched.
Right. Yes. Yeah. There are multiple ways to prove this. Yeah. So in fact, if G minus V is bipartite, then G itself is bipartite. Yeah, that is a true statement. In a matching chord graph, if you delete one vertex and you get a bipartite graph, then the whole graph is bipartite. So in particular in a brick, you cannot delete a vertex and get a bipartite graph. Therefore, you cannot even delete an edge and get a bipartite graph. So therefore, G minus E is not bipartite. So B of G minus E is at least 1. And B of G was equal to 1. So B of G minus E is at least as large as B of G. Turns out this is always true. In general, for removable edges, and this is like, this should sound really strange if it's the first time you're seeing it. Like for removable doubleton, you always go down by 1, but for removable edges, you can actually never go down. You can only stay the same or increase. Very strange. But as they say, truth is indeed stranger than fiction. So let's write it down. This is 9.8. This is actually not difficult to prove, by the way. This is actually easy to prove. G is a matching covered graph. E is a removable edge. Then, in fact, I'm going to give this as an exercise to all of you because it's really not that difficult. B of G minus E, we will still prove it anyways, is equal to B of G, is at least as large as B of G. And in fact, same thing holds for B plus P. B plus P of G minus E is also at least as large as B plus P of G. This is what we will prove. What I would suggest is try proving this on your own. DIY. It's not difficult. At this point in the course, it's pretty straightforward actually. This is monotonicity of B with respect to deletion of removable edges. In the proof, note that for bricks we are already done. For bipartite matching chord graphs, you are already done. Right? For both of them, B is 0. So therefore, deleting an edge, B is still 0 in the case of bipartite. Right? In the case of bricks, B is 1, and when you delete, we observe that you can't become bipartite, so B is at least 1. So for both of these cases, we are done. So now, proceed by induction, take a non-trivial tight cut, and see if you can finish the proof yourself. Right? So, use non-trivial tight cut to prove by induction. Yeah. Okay. So these are two results that are coming up. So in some sense, this is also coming up in the sense that we won't prove it today. But of course, all of this raises a question. Does a brick, for example, in all these proofs, we will use bricks as our base case actually. All of these proofs are going to be by induction basically, and bricks is going to be our base case. Bipartite graphs may also be a base case, whatever. That's not too important in some sense. But all of this raises a question. Does a brick even need to have removable classes? Right? Does every brick have a removable class? We haven't proved that yet.
There are minimal classes.
Minimal class is always there.
And bricks are 3 connected.
Bricks are 3 connected. So therefore there is a removable class. Good, we are done. There is a minimal class. Is that correct? There is always a minimal class. And minimal class will contain an even 2 cut if its cardinality was 3 or more. but bricks are 3 connected, so it will not contain even 2 cut, and therefore it will have to be cardinality 1 or 2. So therefore it will have to be a removable class of cardinality 1 or 2, and that goes back to this point. We already proved it. There is a minimal class, and therefore it is removable. Good. Can we make it stronger? Well, we have proved removable class. Is there always a removable edge? Right? That is the next question. Is there always a removable edge? Of course, you will say no. There are counter examples, very small ones that you can see. K4. K4 has no removable edge. Triangular prism has no removable edge. So can we actually prove that every brick except blah 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 has a removable edge? Stuff like that.
9.4 implies if there is at least 2 minimal classes.
9.4 implies that if there is at least
2 minimal classes.
If there is at least 2 minimal classes,
One of them has to be a removable edge. Both can't be double terms.
that's not true, right? Prism has 2 removable doubletons, 3 removable doubletons actually. It proves something about highly connected bricks. If I have a highly connected brick, let's say more than 4 connected, let's say 5 connected brick.
Oh, 4 connected.
If I have a 5 connected brick, then it cannot have 2 removable doubletons, but it may still have 1 removable doubleton, and now we don't know if there is a removable edge. Right? Yeah. Okay. So this is what we will do in the second part. Let's take a break here, and let's meet in 10 minutes. Is that okay? So in the second part, we will discuss the existence of removable doubletons and singletons and bricks. We already know it exists, thank you. But can we say more? Yeah. Okay. Are there any questions or concerns before we stop recording? Okay. So see you in 10 minutes. Thank you.